All right. So the first thing that we'll do today is talk about one of the quiz questions. It appeared on quiz 12 and quiz 13, and the reason why it's on quiz 13 is because it had a low average, so I repeated the quiz. So I assume that static hazards, for you guys to look at how the function is synthesized and be able to look at is there any redundant prime implicant we left out or not. You guys, I believe you guys can do that. But most of the questions I've been getting are regarding dynamic and function hazards. So I'll take a little bit of time talking about these two. So for dynamic hazard, as the statement says, there has to be three or more delay asymmetries from any single input all the way to the output. So if we consider something like this, where you have three inputs x, y, z, and you have the output f, we are going to try to ask ourselves how many different delay paths are there from any input all the way to the output. Well, if you look at x to f is only one path, so we don't even have to worry about x. The same way from y to f, there is just one path. We don't have to worry about that. But for z, because there are two paths, let's try to take a look. From z to f, one path is through not and or, and it'll have one timing. And the other path is and or. It'll have a different timing because a not gate is absent over here. So this would count as a situation where there are two asymmetries all the way to the output with respect to the input z. Now, this still doesn't qualify the condition that there has to be three or more for a dynamic hazard to happen. Remember, a dynamic hazard looks a little bit different, right? So it looks something like this, where there are multiple transitions at the output only when the input changes once. And this can only happen when there are multiple delay paths, three or more, all the way to the output. So if I come back here to this circuit that we were talking about, Z has two asymmetries, still not uh, three or more. So you would conclude for this circuit that dynamic hazard is not possible because of that reason. Now coming to function hazard, it has to do with two or more inputs changing at the same time. When two or more inputs change at the same time, there will always be a possibility that a function hazard occurs. So for you would answer function hazard may occur in that situation. So I hope that answers your question regarding identifying the type of hazard. Let us come back to the lecture for today. So we'll start off as usual with announcements. Homework 6 is due the coming Friday, October 23rd. You guys are working on Studio 5 that involves decoders and encoders. And I assume that many of you have taken a start on, give me 1 minute, Sierra. So for Studio 5, I believe many of you have taken a start on task 1, which has to do with decoders. Today we'll also talk about encoders, so you guys can fully answer Studio 5 after this. It's due October 28th. Quiz 13 is on grade score for you guys to answer. There's another question on a related question regarding hazards on the chat box, so let me answer that. Can you clarify what input change means? What I mean by that is any input that is changing, for example, Z, right? I'm changing Z and I'm monitoring F. I may have some expectation of F. F has to be 1 or F has to be 0. I may have certain expectation depending on the function that F should be this. So for example, over here, no matter what Z is, as long as I hold X and Y to 1, F should be 1. So when I say input change, I mean this, right? No matter what Z is, 0 or 1, as long as I do not change X or Y, F should be 1. So if I keep changing Z, changing the input Z, do I get an unexpected output or not? That is really the question for a hazard, right? And if a unexpected logic output happens for F, then you say a glitch can occur, or a glitch occurred already, right? So it's in the context of the input changing. So for example, over here in this diagram, I'm not changing X, I'm not changing Y, I'm only changing Z. If I look at this dynamic hazard, a single input has to have a 3 or more delay asymmetries. So you are holding all the other inputs constant, and then you are looking at the unexpected output F with respect to only one input changing. Now in the diagram that we looked at, we were only looking at it with respect to Z, but you could in general look at any input that you are changing while holding the others constant. But for the function hazard, you look at two or more inputs changing at the same time. So you're not holding anything constant. You may hold one of them constant, but you're changing more than one input at the same time. I hope that clarifies the question. All right, let's come back here. So we talked about the announcements. Let's get into the decoder. So this is continuation of where we left things off. We were talking about the 2 to 4 decoder. We looked at the chip 74X139 in the previous class. So this was the complete 74X139, which had two 2 to 4 decoders with active low enables, active high inputs, active low outputs. So that's what we looked at in the previous class. Now we are going to extend that conversation to a 3 to 8 decoder. So the number of inputs are 3, the number of outputs are 8. And in this case, you have 3 enables. As you can see, let's see, let me highlight these. You have 3 enables. And if you are asking the question, why do I need 3 enables? Just hold on to that. That's a very good question, and I'll explain you why we really need it in a certain application. Let's see. Are these any different? Well, clearly G1 is active high enable. So it is enabled only when G1 is 1. And G2A underscore L and G2B underscore L are active low enables. So they have to be zeros in order for the decoder to be enabled. So in terms of enable inputs, we have 3 of them. One is active high, the other 2 are active low. Now, if I wanted the decoder to be enabled, what should I assign these 3 enables to be? Well, clearly, I need a 1 for G1. 100 is absolutely right. So I would need 1 for G1 and the other 2 should be low, active low. And if I set up things like that, you can see what happens due to this inversion and double inversion, right? 1 goes through, it becomes a 0 there, and it becomes a 1 there, right? Because there's another bubble. And then 0 goes through, it becomes a 1 there. 0 goes through and becomes 1 there. So if I have 1 and 1 and 1, I get a 1 there, which is the overall enable signal that is being fed into all the other 8 NAND gates. So one of the enable inputs is held to 1. Now, clearly, if any one of these enable inputs is inactive, then all the inputs to the NAND gates would be, one of the inputs to the 8 NAND gates would be, that's a NAND. Oh, yeah, this is NOR, yes. This is a 3 input NOR. Let's see. All right, so that's as far as the enables are concerned. Now this particular enable master enable line is going to be connected to the input of all the 8 NAND gates. Now let's take a look at this. What are the inputs? ABC. Inputs are still active high. So you have active high inputs called ABC. What about the outputs? Active high or active low? Active low. All outputs are active low because of the naming scheme underscore L, right? And also the fact that we used a bubble at the output here, that's what converted our min terms to max terms. We talked about that in the context of 2 to 4 decoder in the earlier lecture. Now, let us do some kind of simple exercise here. The question is, the first question is, which one is least significant input and which one is the most significant input? So out of these three, A, B, and C, which particular input is going to be least significant? Is it, so Muhammad says A is least significant, and he's absolutely right. And we'll check this. C is actually the most significant. Now we will check this by considering a simple input case. Let us see what happens when my A, B, C are 1 and 1 and 0. Right, so I'm just taking an arbitrary input 1, 1, 0 for A, B, and C respectively, and I'm going to try to find out which particular output is going to be active. Because remember, only one output can be active at any given time for a decoder. So the question is, which output is going to be active at this point? So let's try to, do this simple, do this from scratch. 1 becomes a 0 there, 1 becomes a 0 there, 0 becomes a 1 there, right? And then where is this connected to? That 0 and that 0 and that 1. Where is that connected to? Now, if you look at all the other inputs, so let's see. If I focus on this, can you explain why there is a double NOT gate rather than just a direct connection? Yes, so it's the same conversation about input. Let's see, it's input buffering. Remember, these are coming from. You would expect them to come from uh, another logic module before this. So in order for us to make sure that the logic levels are maintained very well at high and low, you can use input buffering so that your logic levels can get solidified. Yes, it is input buffering, yes. Let's see. All right, so that is 100 becoming 011. Now, if I focus on this particular NAND gate, you see this input here. Let me draw this. Where is this input coming from? This guy is coming from here. Next, you have this guy coming from here. And the next one is coming from here. Now, as long as it is enabled, so let me use a different color for enable. That is enable. So as long as it is enabled, that particular green line is going to be 1, but all the other lines only for this NAND gate are also going to be 1. You see this, this guy here, 0, it becomes a 1 there, right? And that guy 0 becomes a 1 there, and that 1 is already a 1 there. So you get all ones only for this particular NAND gate. For all the other NAND gates, you are going to get at least one of the inputs to be a 0, which will make that output inactive. So the answer here is only this guy is going to be active, meaning low. All the others are going to be inactive, meaning 1. Now we can answer this question, which one is least significant and which one is most significant. Now you see, why 3? What is 3? 3 is 0, 1, 1, right? So this is the least significant input. That is the most significant input, meaning the most significant input has to be a 0. That's what we see for the case of the input C. Questions about this? Now, I suppose in this same logic, I can give you any combination of ABC, and all you need to ask me is it enabled or disabled? And you would be able to tell me what is going to be the output. Let's see, if I go on here, let us do a similar exercise with this one. So here what we have is the standard chip 74X138. The insides of this chip are sketched over here. That's what we have inside that chip. 3 enables, 3 inputs, active high inputs, and uh, 8 active low outputs. Let's see, there's a question on the chat box. Can you go over when the enable is turned on? Yeah, so enable it is turned on. There are 3 enables. One is active high, the other 2 are active low. So if I want the decoder to be enabled, I need to make G1 1 and the active low enables low 0 0. So that's when your output of this 3 input NOR gate would be a 1 only in that particular case. Let's move on here. All right, so you have 74X138, the same configuration here. 3 enables, one of them active high, 2 of them active low, active high inputs, active low outputs. So what we'll do here is I will give you guys a certain combination of inputs and you tell me this. The question is which pin number is low? Question. When the input is 1 0 0 1 0 0, which pin number is low? Pin number or pin numbers? So there are 2 answers right now. We are going to have to pick. So pin number, guys. So look at the pin number on the IC. Okay, so there are now 3 answers. Let us see. All right, so yes, 011, right? If you look at 011, first you would have to arrange those inputs from most significant to least significant. We already said C is the most significant input. So if C is the most significant input, you would not read this as 100. You are literally looking at it as 001, which in decimal is 1. So y1 underscore L is going to be active in that case. If y1 underscore L has to be active in that case, this guy is going to be, pin number 14 is going to be low in that case. Do we just flip the input since output is active low? Yes. So we don't flip the inputs. The inputs are going to be going as is. It has no connection with outputs being active low. You are just reading this as 011, most significant to least significant. So the answer here would be which pin number is low? Pin number 14. Now let's do something different, and for the thing that is different, we will use a different color. What about this? Same question. Which pin number is low? For the input case in red. All will be disabled, yes. Which means none of them are going to be low, yes. Because I disabled it, right? G2B, the enable is inactive. That's it, that's all I needed. So all of them are going to be disabled. Questions about this? Now there are two connections on this IC that are not being shown. What are those connections? VCC and ground. Perfect. So VCC and ground are implicit, but they have to be given, right? They have to be, the power supply has to be on and the chip has to be grounded. Only then it will do these things, right? Okay, let's move on to cascading decoders. So the goal over here is to take two 74x138 chips. So this is a 328 decoder here and a 328 decoder here. And what we are doing is we are making a 4 to 16 decoder by cascading two 3 to 8 decoders. And in this example, you can really see the usefulness of the three enables. Remember, we said we have three enables, one of them active low, two of them active, one of them active high, two of them active low. You will really see the usefulness, the application of multiple enables in this particular case. I've already we are already seeing that the inputs and outputs are connected to do this particular job. So let us now see how. First of all, let us see what this is going to be doing. Let's do the top 74x138 chip first, and then we'll talk about the bottom one. If I zoom in on this, G is connected to high using a pull-up resistor. So that's good. That enable signal is already active. So this is fine. G2A and G2B, the two active low enables, are actually connected to, one of them is connected to one of the inputs N3, and the other guy is actually connected to a master enable signal, enable underscore L, which is going to be for the overall 4 to 16 decoder. So let me just write this. This guy is for overall enables input, which is also active low. Next, let's go on to this, the bottom one. G1 is coming from N3, the same input that went to G2A. G2B is connected to ground, so that's activated, right? That's enabled. G2B is good, that's active. G2A is connected to our master enable. Now, once you see this, let us try to put some arbitrary inputs and look at this 4 to 16 decoder. Actually, what will be helpful is let's try to essentially uh, write out a table for our 4 to 16 decoder. So what I can do is I can have, come on, I need you to draw a straight line. My inputs are N3, N2, N1, and 0, right? 4 active high inputs. And in this case, it is very easy to identify which one is least significant and which one is most significant input, because the numbering itself gives that away. So N3 has to be the most significant because of the index. What are my outputs? Well, my outputs are from 15 all the way to 0. They are all active low outputs. So let me write that down in this fashion. Y15 underscore L, y14 underscore L, and it'll go all the way down to y2 underscore L, y1 underscore L, and y0 underscore L, right? So when I have the situation where all these are 0, so let's see, which, and you assume that this is enabled. It is enabled. Assume that. Which particular output should be active right now? Y0, right? So Y0 should be a 0 and everything else should be a 1. And then similarly, when you go to the next case, what do you have? You have 0, 0, 0, 1, right? What would happen to the outputs? Which output will be active? 0, 0, 0, 1. Which output is going to be active? All right, Y1. So I need to put a 0 there, and I need to put 1s everywhere else. Now, this pattern is going to continue for only half the time. So I'm going to draw a separator here. I'm essentially going to draw a separator here in the middle, and then see what happens in this pattern, because this guy is going to keep moving left, right? That 0 is going to keep moving left as long as the inputs are 0, 1, 1, 1. So that will correspond to the last one will correspond to y7 underscore L, right? So that would be the output of the top 74X138 chip. You see what happens? For the top 174X13 chip, my N3 is 0. And as long as my N3 is 0, the three other inputs, N2, N1, and N0, are literally going to give me which particular output is going to be active, right? 0, 1, or all the way down to 7. In the same way, what are my remaining 8 input combinations? The remaining 8 input combinations are simply going to be 1, and then the sequence is going to repeat, right? And over here, my N3 is 1. N3 basically, you got it, yes. N3 basically determines which chip is enabled, yes. And my 0 during that time is going to move from here all the way to here. So that would be for the bottom 74X138 chip. So we are essentially using, as Jeff pointed out, N3 as something that controls which chip is enabled. Now, if this is what we desire, let us see if that is what we are doing here. You see, N3, when it is 0, this guy is enabled. And when it is 1, this guy is enabled, the bottom one, right? That's exactly what we wanted, provided our overall enabled signal is 0. And N0, N1, and N2 that go into least significant to most significant, least significant to most significant, they are common to both the chips. That's exactly what we wanted. 0, 0, 0, 0, sorry, 0, 0, 0 down to 1, 1, 1, and again 0, 0, 0 down to 1, 1, 1. Now, just so that we understand this really well, um, let us try to uh, do some exercise. Let us say our enable input en underscore l is 0, and our number n is 1011. The question is, which output pin is low? So you would read n as n3, n2, n1, n0. So this would be n3 here, n2, n1, n0. So let's answer this first. Which chip is going to be active, the top or the bottom one? Which chip is active? The bottom. All right. So I, if the bottom one is active, I don't even have to look for this. I can just focus on the bottom one. And the reason why the top one is disabled is because N3, which is 1, is connected to an active low input. So the top chip is disabled. We are done with that. Now let's come to the bottom. G1 is coming from N3, enabled. G2A is coming from enable. We already have that as enabled. G2B is hardwired to ground, so enabled. So the bottom chip is enabled, and you guys are absolutely right. Now next, let us take a look at what are A, B, C going to be. A, B, C are going to be N0, N1, N2. What are N0, N1, N2? N0 is 1, N1 is 1, and N2 is 0. So with respect to the bottom chip, it's going to be what? 3, right? 3 is the 0, 1, 1. That's the value. So Y3 underscore L, that's the one that is going to be active. So we are looking at pin number 12. That is going to be active. All the others are going to be active, meaning, let's see, this is going to be a 1, 1, 1, 1, 1, 1, 1. Everything is 1 except for this equals 0. Uh, Tyler has a question. Can you state why the top is disabled again? So let's see. If you look at N3, N3 is 1, right? So if N3 is 1, let's go and take a look at this guy here. N3 is 1. It is connected to an active low input. So if I make this high, then the G2A enable is inactive, disabled. Is it just because of the not? Right. So it's because of this guy, which is essentially indicating that that's an active low enable input. But in this case, you have connected it to an active high enable input. So if N3 is 1, this guy is good, and this guy is not. Oh, sorry, I need to put the X over here. So this is, you can really see here that by having those extra enable inputs, we were able to cascade decoders to make bigger decoders. And you can really expand this to a bigger design as well. You can take this to 5 to 32 decoder if you wanted to. All right, next, let us, any last minute questions about decoder cascading? All right. Now let's take a look at a different type of decoder. This one is a 7-segment decoder, very similar to the kind of design you guys did for your Studio 2 in the studios. It has, let's see, one active low enable, then it has 4 active high inputs, then it has what? Uh, all outputs are active high as well. This is a standard chip. Uh, A is your most significant and D is your least significant. Now you might say, Professor, how do you know that is the case? We don't know what is inside this chip. We didn't look at it. So how do you know that that is most significant and D is least significant? Because I looked up the data sheet is what I did. I looked up the data sheet for 74X49, and that's what told me that pin number 5, which is A, that is the most significant input, and D, which is pin 4, is the least significant input. All the others at the output are segments, right? A through G. So let us do a simple exercise here. Let us say our input is this. We have a 0 there. We have a 0 there, 1 there, 0 there, 0 there. Now the question is, what are my outputs going to be in that case? So when you see this 0, 1, 0, 0, A being the most significant, then you would literally consider that as that string of inputs, which is essentially 4 in decimal. So 4 in decimal would point to this guy. So let us try to see what happens with the segments for the 4. Where is segment A? Let me write segment A, B, C, D, E, F, and G. Right, those are my 7 segments. So that tells me that A is off, right? B is on, C is on, D is off, E is off, F is on, and G is on. So that's how I would figure out what would be the outputs as long as the chip is enabled for a particular input case. Now, a related question is, what happens when the input provides provides this? What happens then? 1010. What do you think should happen? So this is just a 7-segment decoder. These are the outputs. That's it. There's no other output. It shuts off. Not really. All are disabled. So it's don't care, right? So this is a don't care situation. X. And essentially what that means is some segments might be arbitrarily on and some segments might be arbitrarily off. You don't know. So those are don't care situations. From 10 all the way to 15, if you have an input, then consider them as don't cares. And that would mean that randomly some are off and some are on. All right, so that's your 7-segment decoder. Let's move on to applications of decoders. Actually, before this, I want to make a quick note. Not this, before this. So I want to list out the ways we have seen how to synthesize logic functions. So let me write the question here. how to synthesize logic functions. We have seen many different ways of doing this. The first one on the list is basic gates. We used AND, OR, and NOT gates to synthesize logic functions. Then we said, all right, we can also do this just by using NAND gates. We can also do this just by using NOR gates. What else should I write in this list? How do you synthesize logic functions? Basic gates is one, NAND is other, NOR is the third one, SOP forms and canonical SOP forms is the next. POS and canonical POS is the next one. Programmable logic arrays is one after that. And now we are going to add another way of synthesizing logic functions, decoders. So my claim is that you can give me any logic function and I will show, I will implement that function using a decoder. In fact, we will have an eighth option later on, which is using multiplexers, which is one of my favorite things to talk about. So right now we are doing this. We are going to try to synthesize a logic function, any logic function, using a decoder. So let us say we have a 3-input situation, a function that has 3 inputs. If a function has 3 inputs, then I'm going to need a 3 to 8 decoder to do it, which is what I have right now. This guy is my 74X138. This is a 3 to 8 decoder. And the function that I'm trying to implement is f equals a and b and c, or a and b complement and c complement, or a complement and b and c complement. That's the function that I want to synthesize using the 74X138. What will really help me here is to write the function in, say, a canonical sum of product form. And we can use shorthand for this. So if I wanted to write this f in a compact, in shorthand form, let us say that my inputs are A, B, C in that particular order, what should I fill in the brackets for this function? Two, 4, 7. Yes, 247 is absolutely right. You see this? 1, 1, 1, 1, 0, 0, 0, 1, 0, right? 2, 4, and 7. But the thing to note is A was the most significant, C was the least significant, right? A was the most significant, C was the least significant. That you have to pay attention to that. Only then it is 247. Now what would be F complement? If I said flip it, like F complement, what do you get? Let's see. You have, do you have min terms or max terms here? You have pi max terms, right? if I assume the same order A, B, C, then I have max terms. What do I have in this case? The same numbers, right? 247. Where have we seen this before? Max terms getting ANDed in the context of a decoder. Where have we seen that? Right here. The outputs of the decoders were max terms when we went for active low outputs. So when we had active high outputs, we had min terms. And then as soon as we made them active low, all our outputs became max terms for those inputs. So I can literally take those particular output lines and run them through an AND gate to implement my function. So all I would have to do is, let's see, where is that? Right here. I would have to focus on 2, 4, and 7, right? So I would need 2, where is that? Right here. Where is 4? Right here. Where is 7? Right here. So I would take those 3 lines, put them through an AND gate. Because remember, this is max term 2, this is max term 4, this is max term 7, right? And I put them through an AND gate, so I got product of max terms. And that would literally be my F complement. But I don't need F complement, I need F. So what do? I simply erase this guy and I put a bubble in front of it and I get F. I still need to figure out where the inputs will go. And what about the enables? Well, the enables are easy to figure out because this has to be enabled, this has to be enabled, this has to be enabled, right? So you would connect this guy to, let me draw them. You would take plus 5 volts, resistor, plus 5 volts, connect it that way. Then you would take these two guys and connect it to ground, right? And that will make sure that the chip itself is enabled. Now, what about the inputs? Inputs are a little bit tricky to figure out because when we were writing these numbers 247, we considered A to be the most significant and C to be the least significant. But is that the case even for the chip? Let us try to find out. If I go back and take a look at the chip itself, we said C is the most significant input, A is the least significant input. That's exactly right. So if C is the most significant input, I need to connect this to A, that to C, that to B. That way I get this function in that order, A being the most significant and so on. So I have to connect the inputs in this way and then take 2, 4, and 7, run them through a 3 input NAND gate to get my function F. F, of course, now will be an active high output. Questions about this? So this is how we have implemented the function. We have given 3 inputs, A, B, C. We have got the output F. In the middle, there is a 3 to 8 decoder, enabled 3 to 8 decoder, and we were able to implement the function that way. questions? Okay. Now let's go into the world of encoders. It's exactly the opposite job as a decoder. Are we to get the max terms? So there's a question in the chat box, which not, are we? I'm not able to max terms to find the output combination. Could you clarify that question? I am not sure if I understand it. Can we use OR gate to get F? Okay, so you can use OR gate, but you would have to do this, right? One way to implement a function is this way. The other way to implement a function is, so you can do, one way is product of max terms, right? That's what we just did. We did a product of max terms because the outputs of the decoder were already max terms. The other way of implementing a function is to do a sum of min terms, right? Well, to get a sum of min terms, first you would have to convert the outputs of max terms into min terms. How do you do that? You have to complement them, right? So if you have this 74x138 chip with max terms coming out, you would have to first convert them into min terms. So meaning you would have to add a bubble again. That way you get min terms now. And then you can do the sum of min terms to get F. But and then you would have to connect them to OR gates, whichever numbers. But you see, what is this? If you look at this, what is that? That is no, that is essentially a NAND gate again, right? So that's what we had earlier. If it was active high chip, we can use an OR gate. Yes. If it was an active high, then you have min terms, and then you can use OR gate. But if you have active low outputs, those are max terms. And if you want to sum them, then you would have to use, you have to first convert things into min terms. And after you convert things into min terms, you have to put them through an OR gate, which is essentially the same thing that we did using a NAND gate, right? That's what we had here. All right, let's go on and take a look at encoders. So the story is going to be kind of the opposite of the story for the decoder. For the case of the decoder, we had n inputs, and the general decoder had 2 to the n outputs, 3 to 8, 4 to 16, 2 to 4, and so on. And the encoder is exactly the opposite. So 2 raised to n inputs, n outputs. So you are think of it like earlier you were getting a binary code and you were giving me the decimal equivalent of that code. Now you get a decimal equivalent of a code and you are converting that into a binary code, encode that decimal number. However, there are some constraints. For the decoder, you guys remember we said only one output has to be active. Only one output can be active. for a decoder. And whose responsibility is it? Who takes the responsibility of that? The designer is going to take the responsibility of that, not the user, right? The user can give it anything it wants, 011, 101, like any input sequence. But the designer has to make sure that one of the outputs is active at any given time, only one. But now the inputs are in the control of the user. So we have a problem now, because you can blame the designer here, but you can't blame the designer here, because the constraint, the limitation still exists. Only one input can be active at any given time. So who has to take the responsibility of that? Well, the user has to be responsible now. The user has to take the responsibility that only one input is active. Well, that is a problem, right? Because what if accidentally, without the fault of the user sometimes, and it may be negligence of the user sometimes, what if two inputs or three inputs become active? What happens then? We will need to establish priority. If more than one input becomes active, then the encoder has to establish priority and say that I am going to prioritize this particular input and I'm going to ignore all the other inputs. Hence, we have encoders in two different types. One is a basic encoder, which puts a lot of pressure on the user to get things right. But there is also a priority encoder. The priority encoder has priority inbuilt. So even if the user gets something wrong, meaning more than one input high, active, it'll take care of it. It'll prioritize one of the inputs only and then ignore the other. That is why we have two variations of the encoder, basic and priority encoder. Let's take a look at the basic encoder. So what I'll do is I will try to lay out the truth table of a 4 to 2 basic encoder first. And the truth table is going to be similar to what we had before. We have, say, 4 inputs. Let me call them I3, I2, I1, I0, and I have 2 outputs. Let me call them Y1 and Y0. We see the significance here. Most significant input I3, least significant input I0, most significant output Y1, least significant output Y0. 4 inputs, 2 outputs. We are assuming that all inputs and outputs are active high. So that's an assumption. All inputs and outputs are active high. And we are assuming that this is enabled encoder. And it is a basic encoder, so the user can only have one input active. What are the possibilities? Well, this guy could be 1, or this guy could be 1, or this guy could be 1, or this guy could be 1, right? Only one of them active. Everybody else has to be inactive at that time. The user has to make sure that only those places are active, only one input active at any given time. Now, how does the 4 to 2 basic encoder work? Well, when I0 is active, it will encode that as 00. When I1 is active, you would encode that as 01. When I2 is active, you would encode that as 10. And the last one, I3 is active, you would encode that as 11. Exactly the opposite of what a decoder did. Uh, let's see, would the chip just shut off with more than one input? Well, it would not shut off if you really so basic encoder is just it's not a practical thing for you to use. In practice, in reality, we will always use priority encoder. But to be able to start talking about a priority encoder, we need to first talk about a basic encoder. That's what we are doing. Let's see. All right, so that's your truth table for a 4 to 2 basic encoder. What do we do after we write a truth table? We write logic expressions for the output. So what would you say the logic expression for y0 would be? And y1 would be? So you guys tell me the logic expression for y0 and y1. It's going to be very simple. Just ask yourself, yeah, exactly. Y0 is 1 at only two situations. I1 has to be on and I3 has to be on. So you would literally write I1 or I3, right, for Y0. And then for Y1, I2, let me see, for Y1, you would have this edge, this is 1. So I2 is 1, I3 is 1. Done. That's how you are going to implement a basic encoder. 2 OR gates. That's it. That's all you need. 4 inputs, 2 outputs, 2 OR gates. That's all. Do you see something troubling here? When you see this, do you see something a little bit confusing? Anything that bothers you in this? I0, yes. I I0 is not connected to anything, right? So for a 4 to 2 basic encoder, I0 doesn't even matter, right? If this is 1, like it doesn't matter in this case. Now let us take a look at the priority encoder. Same, 4 to 2. 4 to 2 priority encoder. We are going to assume, we are going to consider the same sort of inputs. Let me take it over here and make this here. All right. But in this case, I'm going to have to consider the possibility that more than one input is active at any given time. So for the first case, that is okay. I0 is active, and when I0 is active, you get the output 0, 0. But in the second case, you get I1 to be active, but what if I0 was also active? What if this was also active, 0 or 1? Well, in that case, we are going to prioritize, we are going to give priority to I1 and encode that as 0, 1. So you see priority over here is being given to the most significant active input. So if I1 is active, you would give I1 the priority. You would not give I0 any importance. You would encode that as 0, 1. Next case, these three. Next case, these three. X doesn't matter, doesn't matter, doesn't matter, doesn't matter, doesn't matter. So you see, if suppose I2 is active and I3 is 0, that's it. You don't even have to look at I1 and I1 and I0. As long as I3 is 0 and I2 is 0, you would give priority to the most significant active input, which is in this case I2, and you would encode that as 1, 0. So I hope that you guys see how this priority is being established in the sense of a truth table. Give priority to the most significant active input, and that's it. Now, assume that we have an enabled situation. Our encoder is enabled. We are going to do something slightly different compared to the previous case, because now we have don't care situations. We are going to write row expressions. So for each row, we are going to write a particular expression. So for example, for the first one, we are going to write H0. H0 is going to be active, H0 is going to be 1 when I3 is 0 and I2 is 0 and I1 is 0 and I0 is 1. So the expression for H0 is going to be, let's see, I3 complement and I2 complement and I1 complement and I0. Similarly for next one, H1, I3 is 0, I2 is 0, I1 is 1, and I don't care about I0. Next, I3 is 0, I2 is 1, and that's it. I don't care about I1 and I0. Next, H3 is simply I3. In this case, all inputs and outputs are active high. Now let what happened here? Are you guys able to hear me?
Yes.
Okay, well, for some reason, everything started echoing. Okay, so Y0, what would be the expression for Y0 now in terms of uh, row expressions? So instead of adding I1 and I3, I2 and I3, I would add H, right? So for Y0, you have H1 or H3. And for Y1, you have, let's see, H2 or H3. And again, you have all inputs and outputs are active high. All inputs and outputs are active high. So what we did over here is still don't care H0. Yeah, we still don't care about H0. Yes. So by looking at 4 to 2 basic encoder and a priority encoder and being able to write the expressions, now when you start looking at an 8 to 3 encoder, this is a 8 to 3 basic encoder. You guys can really see the pattern develop. So for example, the number of inputs are 3, the number of outputs are 8, which is why you have a 8 to 3, right? 8 inputs, 3 outputs. The inputs are I0, I1, I2, I3, all the way to I7. We had just 4 of them in our example. Outputs are 3 of them, Y0, Y1, Y2. All are active high, right? All inputs again and outputs are active high here. How are they connected? A simple OR gate. In our example, Y0 was simply I1 and I3. In this case, it's going to be I1, I3, I5, I7. Y1, we had I2 or I3. In this case, it's going to be I2 or I3 or I6 or I7. Because literally that's what happens, right? If you expand this table, instead of 4 things to 8 things, and instead of this from 0 0, instead of 0 0, this being 0 0 0 and 0 0 0 0 0 0 all the way to 1 1 1, you are literally saying the least significant output alternates, the next to that goes half the speed, and so on. So those numbers are essentially going to be 1 3 5 7 alternating, 2 3 and 6 7, right? 2 off, 2 on, 2 off, 2 on, and then 4 off, 4 on. And the same way as before, the least significant input is left alone, is hanging. It's not connected to anything. So if you understand the 4 to 2 basic encoder, we have just expanded it over here to 8 to 3 basic encoder. And the problem still continues here. This can just be like a you know something that is theoretical. I cannot put this into practice because there is no way to guarantee that only one input is going to be active, which is why we need a priority encoder. So that's the encoders themselves are used a lot in real applications, right? So for example, if you have a service and many people are requesting for that service, say you want to encode each person coming in and requesting for service, you want them to get a particular number, right? So you could use the request. One of them comes in and presses a button, for example. Requester 3 presses a button, for example. Requester 3 comes in and asks for service. He presses a button. What would happen? He would get a number, right? 011, right? Your number is 3. Probably not for the same reason, but the point here is uh, this can be used in real applications where you want to associate like a number with different people asking for service. We move on next to the 8 input priority encoder. Exactly the same way as we did 4 to 2 priority encoder, now we have 8 to 3 priority encoder. 8 inputs active high, 3 outputs active high, and there is one more one more active high output called idle, which becomes active if none of these inputs are active, right? So it's saying I don't have any input active at this time, so I'm idle. So idle would literally be the OR operation of all the inputs complemented. So literally a NOR operation, which can be written using De Morgan's law in this way. Now, where did all these expressions come from? The same way we derived row expressions for the previous example. So these are all what we called row expressions earlier, right? We had H3 as I3. See this? H3 as I3. Now we have H7 as I7 in the case of 8 to 3. And then H6 will be I6 and I7 complement. And then so on. You go down this list all the way to H0. But when you put the row expressions together to get the outputs, in this case you are calling it A2, A1, A0, we called it Y2, Y1, Y0. You have 1, 3, 5, 7. We had just 1 and 3 for the least significant active high output earlier. Then 2, 3, 6, 7, we just had 2 and 3. 4, 5, 6, and 7, we didn't have this output earlier. Again, H0 is not appearing here, right? H0 is kind of not connected to anything. But I suppose if you look at the 4 to 2 priority encoder truth table and logic expressions, you will be very easily able to expand that to the 8 to 3 priority encoder, the relationships here. The idle output is indicating that, let me use this, there's no active input. So it's like, did you get something or not? So got something or not. So that output can be used to find out whether any one of the inputs are active or no, they are not. And that takes us to the standard 8 to 3 priority encoder chip, which is 74X148. So this was kind of a theoretical. Now I0 matters. Yes, I0 would. Hold on. Only for the case of idle it would matter. Yes, but not for H0. Yeah, it would not for H0. Hence, it would not for any A0, A1, A2. All right, now let's take a look at this. So the priority encoder conversation that we just had for 8 to 3 case, that was just a theoretical example. This is not a chip. 74X148 on the other hand is an actual chip. It has one active low enable, 8 active low inputs, 3 active low outputs, 2 other outputs called got something and enable output. Now that we are out of time almost, we will stop here, and when we come back we will pick up with this, and then we will try to relate this to the truth table for 74X148, and then we'll get into the tri-state buffers, which is our next topic. That's in the next class. All right, I'm going to stop recording here.